comes in many shapes and sizes. That's why it's important that we know what are called parent functions or certain shapes in order to help us analyze that data and find a mathematical model that will match with that. So let's go ahead and look at specific data shapes, and then we'll use that in some data sets to try to find our own mathematical models.
These 5 parent functions are important. Probably most familiar with the line graph. If we take out the constants m and b, we can say that y is directly proportional to x. Any Plotly graph, you can retrieve the data by clicking on View Data. This will bring up the original values. Then, if you want to isolate a subset, you can choose new x and y variables to create a scatter plot. This graph has a y is proportional to x squared relationship. We also call this polynomial. In other words, y is proportional to x squared. As my x increases, so does my y. But it is not linear because it's increasing faster in the y direction because the x is squared. The next graph we're going to look at is where our independent variable is proportional to the square root. Y squared is proportional to x, or y is proportional to the square root of x. The square root looks similar to the polynomial, however, it's flipped sideways. The inverse function, y is proportional to 1 over x, and the inverse squared function, y is proportional to 1 over x squared, look very similar. Here we have the inverse and inverse squared. Notice that the inverse has lower y values previous to 1. Inverse squared has higher values previous to 1. You would use curve fitting to figure out which one is which. As we get closer and closer past, you see that the inverse squared will decrease quickly with values greater than 1. Here we have some data that looks pretty clearly linear. As height increases, weight also increases, as we would expect. Adding a fit is simple in Plotly. Click Add Fit to this trace, and linear is already a built-in function. Doing so will give you important values such as your r squared value, your slope, and intercept. I like to add the results as an annotation so that I can get my equation right here on the graph. This equation is then editable if you want to put in the correct variables such as weight and height. Then when I click away, now my model shows the proper variables. This data set was imported from an Excel spreadsheet by going to upload a file. Here we're going to look at the foot smell effect on the visitors in your home, measured in European odor units. Add fit data. The question is, will this be an inverse or an inverse squared? We know it's not one of the other ones. So let's go ahead and try an inverse squared first. And with this, there's some sub-selections. I want to use one of these because it allows for any shifting and or in the y or x direction, and it has the constant in front. So I'm going to run this fit, and I get a pretty decent value, 0.99. So let's go ahead and add that, 0.9976. Now let's take a look at what if I add another fit, an inverse function. And I run the fit, and I get an r squared value of 1.00. Perfect. So in this case, I'm going to say that the inverse function is a better model than the inverse squared function. So how do we deal with this now that we have two fits? You go ahead and get rid of the one that has the lower r squared value, close out, stylize your graph, and share it. All right, here we have a graph of Colossus versus Zerglings. I've already gone ahead and put in a linear fit. We can see that it's not a great fit with 0.94 r-squared value, and we see that the line doesn't really match up with the points. So from our previous section, we know that this is a y-squared or square root function. Currently, Plotly doesn't have a defined square root function in here. So what we can do is define our own function. We can say some constant multiplied by our x values, which is Zerglings, to the 0.5 power plus some y shifting. I know that there's no x shifting in this particular case, but if there was, you can add a shift in here like so. You can enter different guess values, and then you can show your guess on the plot, but I find that once you just run the fit, it'll hone in on what the exact numbers are, and you'll be better off that way. So here, we find that we get an r-squared value of 1.0. Obviously, this is made up data, so let's take a look at what we've got. I want to get rid of the fit that didn't work, and then keep the one that I have. Save your data, make any changes to the y and x variables, and then share it with your professor. Notice a couple of things. If something is times 10 to the negative 9th, that's equivalently 0. Thanks for watching. I hope you enjoyed this video. You can find others like it at mrpfeiffer.com. You can also find more resources at plot.ly/learn. Hope to hear from you soon, and I'll see you guys next time.